Hey everybody, it's Mr. Bronze coming at you from Studio 63. Just put together a video for today, our short week, Monday and Tuesday. Move you guys along with Chapter 12, our probability chapter. I know we jumped quite a number of chapters. We went from 5 to 12, but I thought this was a better order for our topics for this year. Just as a quick note, thank you for those of you who have reached out to me with the kind words and emails and messages with regards to my wife's surgery. I definitely appreciate that. It was very nice. She is still in the hospital as of today, which is Sunday. We're expecting to bring her home tomorrow or Tuesday the latest. So keep your fingers crossed and get her out of there and get her home and on the road to recovery. All right. So last week on Friday, I had you watch a video that discussed both permutations and combinations and kind of started things off with word problems. I think they're a little bit less rigorous than some of the other types of questions we can ask with permutations and combinations. So we're going to take a step back right now and just focus today's lesson on permutations. So if you do remember, as you already know from Friday, a permutation is an arrangement of objects. And the key is with a permutation, order is important. Okay, so that means given the situation that you have, whatever that situation might be, that if you change the order, it changes your answer, okay, or it affects your answer. So we're going to begin by looking at a specific situation. So here it is. We've got Alan, Cassie, Maggie, and Roger. So 4 friends. They want to take a photo in which 3 of the 4 friends are lined up in a row. So they're not all going to be in the picture together, only 3 of them. I guess one of them is taking the photograph. So how many different photos are possible? So we want to sort of make our first step and think about, well, what are the possible lineups? Let's really break this question down. So instead of talking about a formula for permutations or talking about using the calculator for permutations or any of that other stuff, let's just kind of consider what our options are. So if we make a list, and here it is. So what I did was I used the first letter of everybody's name, and I ran through all of the possible lineups for the friends if they're taking a photo. Now, certainly, if you go from left to right, like here we have Alan, Cassie, Maggie, that is different than if we have Cassie, Alan, Maggie. It's the same 3 people, but the way they've arranged themselves as they're posing for the photo is different. So it's going to be a different photograph. So what that means to us is order is important in this case. We've got ourselves a permutation. So we can see there are 24 possible lineups for the photo. So here's the thing. This was only arranging 3 different items, 3 different names. And if you sat there and put this list together, it's going to take a little bit of time. Think about what would happen if we used all 4 friends. The list would be much longer. What if we blew it up to 5 friends, 10 friends? So then it really becomes very time consuming. We don't want to do that. So permutations themselves and how we evaluate permutations really help to get you to the same answer, but a little bit more quickly, as opposed to writing out all of your options. So whoever's in the room for my class, if you need to pause this video for a second for everyone to get this list down, that would be awesome. Thank you. All right. So how do we use permutations? Well, the first step we have to decide, is order important? And we decided the order of the friends for this question was important. So now that we know that, because we know we can take the same 3 friends and rearrange their order and make it a different photograph. So this is what this little explanation is here that I put together. Think about what I said before. If we have a photo that shows Alan, then Cassie, then Roger from left to right, it's different than a photo that shows Roger, then Cassie, then Alan from left to right. Same 3 people, but a different order. It changes the photograph. So that tells us the order is important. So now we know we're going to use a permutation. So with that said, permutations use multiplication. So that's a real simple sort of overview of permutations. Yes, they use multiplication. There's a lot of other little detail things that go into permutations. And we're going to spend some time both today, tomorrow, and then when we get back after the break talking about permutations, because there's a wide variety of questions. And if you think back maybe to your time when you first talked about permutations, we had really broken them down. Your math teacher probably broke them down to two different types of problems. This is very common, and that's those that have repetition versus those with no repetition. So we're not going to get into that with today's video. Today's video is really sort of just an overview of permutations themselves, but this is going to play a big role on what we talk about tomorrow. We got to keep that in the back of our mind. Okay. So if we think about this, imagine you're one of the four friends and you're the one who's taking the photograph. So you are the one, you've got your cell phone or you've got a camera, whatever it is, you're taking the picture. You're going to put everyone in order. So actually, you know what? Let's back it up. Let's say there's a photographer there. So the photographer wants to put everyone in order. So he's going to start on the left. And he says, all right, I would like Cassie on the left. Now, before he selected Cassie, he had four different people to choose from. Okay, any of the four. So he puts Cassie on the left. Now, the next person who's going to be in the middle, maybe he selects Roger. Okay, he had three to choose from, and he selected Roger. So first he had four choices. Then he had three choices. Then once he selects Roger, he's down to that last spot in the photograph. There's only three friends that are going to be there, and there are two people to choose from. So then he has two choices. So here, if we use multiplication, look at how we break this down. We're looking at talking about modeling an answer based upon the number of choices we have for each spot. So if we sort of identify our spots, well, that's tremendous. Let's cut that down a little bit. There we go. We've got a person on the left. We've got a person on the in the center, right? And then we've got ourselves a person on the right. And in this explanation for the question, we're really talking about saying, okay, let's put the first person in. I have four to choose from. You go on the left. Now you turn around, there's only three people to pick from. Then you pick one of them to go in the center. And now that you've done that, there's only two people left to choose for who's going to sit on the right. So you're making choices, and we're able to multiply those together. Now, when we get into tomorrow's conversation, we're also going to talk about the fact that there's no repetition here. It's actually impossible to have repetition because you can't put the same person in the left spot and the center spot, or the center and the right. They can only be in one position. So we'll sort of allude to that today, and we'll get more into that tomorrow. All right, let's take a look at a couple of examples and see how we're going to play this. So in how many ways can you arrange 5 math books on a shelf? Okay, so the first thing, is order important? So the answer is yes. Imagine the math books have numbers on the binder, just 1 through 5. Keep it simple. We can arrange them in the order of 1, 2, 3, 4, 5, and that would be different than if we did 2, 3, 4, 5, 1. It's the same 5 books, but if we change the order, it's a different arrangement when you look on the shelf. So order does matter. So this certainly is a permutation. So why don't we note that to begin? Okay, so we've got ourselves permutation. So now that we know that, what we can often do, if we're going to model this out, is just make ourselves a couple of little line segments. Now, how many segments do we need? Well, we need 5 altogether, right? Because we're going to place 5 books on the shelf. So there's 1, there's 2, there's 3, 4, and 5. And what we're imagining is that these little line segments represent the position of the books on the shelf from left to right. So you have the 5 books in your hand. And you say, okay, I need to choose one to put on the shelf first. Well, for your first choice, you can choose any of the 5 books that you have. So you got 5 choices. You say, okay, great. So you pick one of the books and you place it there. You say, well, I need to put a book in the second location. How many do I have left to choose from? Well, you've used 1, so now you're down to 4 choices. Okay. And we're going to start to see a pattern develop. Now we've placed 1, 2 books on the shelf. So now when we go to place a book in the middle position, there's only 3 remaining to choose from. So then we pick a book and we put it there. Next, we're putting a book in the 4th spot. And as we go to our pile, there's only 2 books left because we'd already put 3 on the shelf. So we have 2 to choose from. And finally, in this last position, there's only 1 book left because the other 4 are already on the shelf. So this is how we use modeling to help us get through and set up what we need to do. So let's think about this now. What are we going to do? Well, we said earlier, when we talk about this sort of arrangement and we're lining things up, we're creating a situation where we're multiplying the number of choices we have. So we're going to multiply from left to right. And when we multiply 5 times 4 times 3 times 2 times 1, we have 120 ways that we can arrange 5 math books on a shelf. And there's our story. So if you notice, we had 5 math books to begin with, and we arranged all 5 of them on the shelf, and order was important. So now in example 2, let me change it up a little bit. You've been asked to judge an art contest with 15 entries. And how many ways can you assign first, second, and third place? So now there's 15 people in this art contest, but you're not arranging all 15 of them. You're only arranging 3 of them. You're putting them in an order. First place, second place, third place, right? So order certainly matters. So let's think about what we've got going on. Let's come at this from a modeling perspective. So let's put a couple of line segments. Let's create a couple of line segments here where we can put the number of choices we have for each place. And there's only 3 that we need because we're only selecting first place, second place, third place. So you look at all the pieces of art, and now you're tasked with selecting someone for first place. And how many do you have to choose from? You have all 15. So you find what you deem to be the best art piece, and now you're going for second place. There are 14 entries left over to choose from. And then finally, you've selected first and second place. Now you have 13 different options for third place. So a very similar pattern to before, where we're decreasing by 1 for each one of our values. But here, we're not using up the total number of integers that we started with. In this case, they represented art entries. We're only using the 3. So with that said, we're going to multiply our number of choices together. And here we go. Get my equal sign up here. And I'm going to go for a little assistance here with my calculator because, well, I can't multiply 15, 14, and 13 in my head. So we come up with 2,730 different ways we can assign first, second, and third place. All right, on to number 3. How many 3-letter words? And I also put in there, including nonsense words. So I'm not talking about words in the dictionary. I'm really just talking about putting 3 letters together. So QXZ would represent a word. Okay, so how many 3-letter words can you make from the letters of the English alphabet if letters cannot be repeated? All right, So now we're making 3-letter words. So we have to start our modeling by putting 3 line segments together. So go ahead and arrange those. Space them out a little bit. There we are. Okay, so I can choose any letter in the alphabet to go first. Well, there's 26 letters in the alphabet, so that's how many choices I have. So then I place one of the letters there. Now I want to choose a letter for the second position in my 3-letter word, but I can't repeat letters. I can't make a word that's MMM. So once I choose one letter for that first position, I can't choose it again. So now I only have 25 choices. And then for my third position, or the last letter in my 3-letter word, I've picked 2 letters of the alphabet. I only have 24 left to choose from. And this is why it's so important that for these questions, we really take our time and read carefully. As soon as we see that we cannot be repeated, it says right here, cannot be repeated in the question, then we know that repetition is out, and we're going to have to start decreasing with each choice that we make. So now we're going to use our old friend multiplication again, and we wind up with 15,600 different 3-letter combinations we can make using the letters of the alphabet with no letters repeating. All right, example number 4, we've got Fred, and let's just cover up the rest of this so it's not a distraction. There we go. He's lining up his 4 golf trophies on a shelf. How many different possible arrangements can he make? All right, so he's got 4 golf trophies. He's going to use all of them. So that means we're going to begin with 4 different line segments. So let's get our 4 line segments together. And there we are. So Fred decides to put his first golf trophy up on his shelf. He can choose any of the 4 that he has. So he has 4 options to choose from, and he puts one on the shelf. Then he goes to select a second. There's only 3 there because one's on the shelf. So he chooses one of the 3 options that he has. Now that he's placed 2 of the trophies on the shelf, he only has 2 left to choose from for that third position. And then in the last position, there's only 1 golf trophy remaining to put up on the shelf. So we're doing a little countdown: 4 times 3 times 2 times 1. And do a little mental math. We get 24. All right, so that's our first group of example problems. Hopefully you guys are doing okay with that. Remember, if you have any questions, you can email me or post a question right in the classroom in the stream. I got to get back to you guys as soon as I can. Okay, so what's the deal with repetition? So even though I said earlier we're going to do that tomorrow, I forgot I had added this in at the back end of the lesson. Now, we always want to be on the lookout for repetition. What do I mean by that? Well, sometimes right in the question itself. Let's see. Let's determine how many words. Now, notice I put words in quotations because, again, we're not saying words in the dictionary. I'm just saying we're putting a bunch of letters together. Can be created from the letters in the word books. So here's our letters, B-O-O-K-S. So we've got books. Now, there's a couple things we have to notice. Number 1, this is our repetition piece right here. We see there's repetition because there are 2-letter O's. So we want to sort of make a mental note of that. Think about writing out the word books. I'm going to write it up here. Let's get a different text color. Here we go. All right, so B-O-O-K-S. There's books. Now, if you notice, as we mentioned earlier, there are indeed 2-letter O's. Now, wouldn't a different arrangement of these letters, where we simply swapped the 2 O's, and that would be rearranging 2 out of the 5 letters, but it looks exactly the same. If we take these 2 O's and then we switch them, put them in the opposite order for our second word, these 2 words are the same. There's no way of us knowing which O is which. There's our repetition. So that's what we have to think about. And if we don't think about this, we create double counting. So if we were to count this twice, we'd be counting the same word 2 times, even though it's an arrangement that is different from each other. So we've got to account for that. We don't want an incorrect answer, right? We want to get ourselves a correct answer. So let's see how we address this particular problem. So to avoid the mistake, we're going to use our old friend, Factorial. Now, you may remember what Factorial is. And a Factorial, let's see, let's get a text box going here. Here we go. Factorial is your exclamation point. Yeah, I don't know if you guys remember that, back from your middle school days. Exclamation point. So what does your factorial tell you to do? Well, you're going to see the factorial symbol after a number, an integer. So the factorial symbol says take that integer and multiply it by every other integer less than it, and then stop when you get to the 1. So if I had 3 factorial, I'd multiply 3 times 2 times 1. I'll stop there. That's the basic idea. So here's an example. 5 factorial is simply start with the number in front of the factorial sign, your 5, and multiply by every integer, counting down until you get to 1. So 5 factorial is equivalent to 120. Now, if you are thinking about the calculator, I can give you, you want to first go to your math button. You're going to press that. And then once you're in there, you have to go to the probability submenu, which is all the way on the right. So you use your right arrow to get over there. And then you go down, and I think it might be the 4th or the 5th option in the list is the factorial symbol. So you'll see it there. All right. With that said, let's see how we're going to handle this problem. I could get the screen to go down. There we go. So here's the word moose. So moose is like the word book in that it has a repeating letter O. So there's a very easy way for us to handle this, and this is how we're going to do it. So we're going to first take number of letters in the entire word, whatever that number is, and figure out what its factorial is. Then we're going to divide that by the repetition factorial. So this is going to be our basic, I guess you call it a little formula, little fraction that we're going to use here as a formula, more of a relationship between the total number of letters and those that repeat. So let's look at moose. Moose has 1, 2, 3, 4, 5 letters. So that's what we're going to start with. 5 factorial. Now, what repeating letters do we have? We only have O's that repeat. How many do we see? There are 2 O's, so it's 2 factorial. If it was a word that had 3 O's, we'd use 3 factorial, and so on and so forth. So now, make sure we got to make this into a fraction. Not crazy. You can, of course, evaluate this in your calculator, or these numbers are small enough to think about by hand. Here we'd have 5 times 4 times 3 times 2 times 1 divided by 2 times 1. And if we think about doing some canceling, the 2's will cancel out. So the bottom just becomes 1, and we no longer have to express it as a fraction. So we have 5 times 4 times 3. And we have 60 different 5-letter arrangements that we can use. Here we are. All right, so something a little bit new with this whole repetition thing. Let's see what we got next. So let's try, how about this one? Similar question. I got the word hexagon. Now, there's a difference between example 5 and example 6. In example 5, we had moose. So the repetition of the letter O. Here we have got the word hexagon. There is no repetition. So with no repetition, this simply becomes the number of letters factorial. Because if we have no repetition, every letter appears only one time. So we don't need to worry about it. There is no repetition. So this is number of letters factorial. And in our case, hexagon, Hexagon, has 7 letters. So 7 factorial. Now, again, I would try, if you have your calculators with you, try it now. Okay, fire your calculator up, press your math button, and then you'll see 4 different subheadings on the top, or different menus, submenus to go into. Look for the one that says PROB, short for probability. It's all the way on the right. Go over to that one, and then go down the menu until you find factorial. Now, I should have prefaced that statement by saying you have to press your 7 button before you go into the math menu. All right, so make sure you're doing that, because once you get in there, it's not going to allow you to put what you need in front of the factorial. And there we are, 5,040. All right, rolling right along. How about this one? And I know someone had to have been thinking about this. What happens if we have more than one letter that repeats? Excellent question. Let's break it down. Bookkeeper, Bookkeeper. Hey, that's 10 letters altogether. So we got a 10 factorial. But now we have multiple repetition. Let's work from left to right. The letter B does not repeat. The letter O does, and we see 2 of them. So we have a 2 factorial. Then we see the letter K. There's 2 of those, and then we have to do another 2 factorial. And with the letter E, there's 3 of those. So there's a 3 factorial. And then P doesn't repeat, R doesn't repeat. So now this is what our fraction looks like. Now we want to be very careful with how we enter this in the calculator. So you may want to evaluate your numerator and denominator separately, meaning you may want to determine, well, what is 10 factorial first? That's a pretty large number. It's 3,628,800. Then on the bottom, multiply. And you can, the great thing about the calculator is you don't need to press the multiplication symbol button. You can simply type in 2 factorial, 2 factorial, 3 factorial. And you'll get your answer of 24. Then, when you're ready, you can take your 3,628,800, divide that by 24, and you'll find your solution is 151,200. So, this brings us back to this idea of factorial, but also the basic idea of evaluating in algebraic terms and following order of operations, following our PEMDAS rules. We want to be real careful with that. All right. I think that might be it for us. It is. Okay, great. Well, hopefully this gave you guys a little bit more practice in the world of permutations. I am attaching a homework, or have attached a homework assignment in the stream with our post. So if you have a few minutes at the end of class or when this video is over, I'm sure you will, you can begin that assignment. Whatever you don't finish in class, make sure it gets done at home or later today, and submit that to me by midnight tonight. I'm not sure what I'm doing for tomorrow's lesson yet, if I'm going to be able to make a video. In the event that I'm not, I want to wish everyone a Merry Christmas, Happy Hanukkah, Happy Kwanzaa, Happy Festivus. Whatever you celebrate this time of the year, enjoy, have a great new year, and I will see you all in January. All right. Thanks, guys. Have a good day.